Hello, this is Jeffrey Fox, Unit 2, Lesson 9, Big Data Applications and Analytics course in the Data Science curriculum. And here we're going to look at one of the examples done in detail in this course, which is the discovery of the Higgs particle with the Large Hadron Collider at CERN. This, remember, is the course motivation unit. Here we have a mosaic of information about CERN, and it comes from an article that I wrote with Tony Hay and Andrew Thethan called Where Does All the Data Come From? The link to that is up here. So here we have a picture of CERN. Well, actually, it's sort of superimposed on a map. It's really underground CERN, runs around in two circles, and those particles are collided, and the results of the collisions are recorded by an apparatus, and there are these different experiments: ATLAS, ALICE, LHCb, and CMS are the four major experiments. They all have apparatus like this, although ATLAS and CMS, I think, are a little bigger than the others. And you can see it's enormous. Even though these particles are tiny, 10 to the minus 13 centimeters in size, to actually measure them and study them, you need enormous apparatus, because what happens is these protons collide, and then the results of the collision are fly out, and then they're measured in complicated devices which take charged particles and measure the tracking of these charged particles. This is what you see here when you see these tracks. These come from taking chambers which have looked at the what happens when charged particles go through depositing their tracks in these chambers. And then there are other things such as so-called calorimeters, which measure energies when people hit them and think about photons or other particles hit them. And so these events here are measured on an enormous scale, even though the particles are tiny. And that's just what it takes to produce an accurate measurement, because unless you made it this big, you will not be able to detect the 100 or so particles that came out in this event. When I did this field, we only produced tens of particles per event. Now we're producing hundreds of particles per event because we're at higher energy. And as they bash each other harder, they'll produce more particles. And we have the same number here, which is possibly not so accurate, of 15 petabytes per year. It's in that broad range, whether it's 10 or 40, I'm not quite certain. Notice this tunnel here is 27 kilometers, 17 miles in circumference. So this is pretty big. It crosses Switzerland and France, probably deliberately to emphasize the great collaboration called the European Union. And you have the LHC computing grid, which actually probably has more than 200,000 cores arranged in a three-level structure, which we'll depict in the actual details of this course, where the lowest level is the accelerator itself. It probably processes, I don't know, 25% of the data. Then you have a second level down, which are the national facilities. A place like the US probably has several tier 1 centers. There are big DOE labs such as Fermilab, Brookhaven, and so on. And then tier 2, even Indiana University has a tier 2 system for the so-called ATLAS experiment. Each experiment has separate infrastructures. And so here it has here 7 tier 1, there's one stage for CMS, which is one of the bigger ones, and 50 tier 2. So this is some enormous enterprise. And you're meant to detect, looked at all these particles here and look for signatures of things that are interesting. This is an interesting event because there's a lot of the information going out sideways, which is very unusual. Normally, information just goes back and forth because these particles are going in, which collide, are going like this, and what they produce also goes in the same direction. To produce something sideways is very unusual, and it's typical of the so-called trigger to be able to detect events that are interesting to look at. This data analysis is very sophisticated and again requires theoretical understanding as to what might be interesting. You're not just taking all data, you're looking at data with a very clear bias, which is biased by what you think. And here's a typical accelerator. You can see the tunnel. We saw the tunnel was depicted for CERN. This particular tunnel is from Brookhaven with a so-called heavy ion collider. It's accelerating not protons, but heavy ions. And this one is only 2.4 miles long. Remember, CERN was 27 kilometers. And this one's somewhat smaller. It's not as high energy. The particles are bigger. And it's probing different things. It's probing the sort of gooey things that happen when lots of particles collide with lots of particles, a real mess. And maybe in that real mess, something dramatic happens. All right, here's the typical results of the experiments, and we'll describe how to analyze this type of data. There's a simple so-called histogram, which is basically the number of events of a certain type. These have already been selected to be of the type that looks interesting. This is from the Atlas experiment, one of the two big experiments. And you have here, you're looking at the so-called two-photon decay of the Higgs particle. And so you're detecting two photons probably going out sideways, one in this way, one in that way. And then you look at that, calculate the mass, and you hope to see a peak. Because unfortunately, you can get two photons going out sideways from various reasons, either because they weren't actually photons or just because they're background events, which produce two things. One sends a photon that way, the other one sends a photon that way, and really those photons aren't correlated. And this is the background here, this smooth curve, which you determine from the data. And here you have a bump, which is the Higgs. And this is the model. You produce a model called smooth background plus bump, where the bump is a particle. And then you fit that bump to find the so-called width of the Higgs, which is dominated in this case by measurement errors, and the mass of the Higgs, which is a real measurement, because even if you do measurement errors, the mean of this Gaussian is going to be at the actual mass. And so that's it's not distorted by errors. Folks, let's look at this. This is this bump, which is the Higgs boson. And I still remember, I can still see the chalkboard where my professor, who was an expert in particle physics, which is the field I did my PhD in, I was an undergraduate, and he got up and told me that this was a particle. I was staggered that something like this could be a particle. So I'd entered the field, because the other brilliant professors were telling me how to solve del squared phi equals minus 4 pi rho for all sorts of different applications, fluids, astronomy, what have you. And I found that sure was boring compared to this being a particle. Wow. And actually, it's sort of interesting that this is the same technology being used essentially today to find the Higgs, as was actually in 1964. It's the same technology I used in my research until around 1980, when I left that part of physics. And it's sort of interesting when we have these amazing new developments like deep learning, that still this bump is responsible for the major discoveries in the area which gets the most data, and is possibly the most fundamental. Of course, the reason is this is small data. The bump is not big data. There's lots. The whole amount of data in the experiment is astonishingly big, but this is needles in a haystack. So, actually, after going through and getting my PhD and understanding more about bumps and particles, I went into computer science and informatics and engineering, partly because I was amazed by the size and physics activities. I mean, the team that does Atlas, we have a The slide on that a little later on has 3,000 physicists at 175 institutions in 38 countries. This was 2013. It's probably not changed a lot. The size of the experiment's unchanged. 45 meters long, 25 meters in diameter. We have a picture of it earlier on, do we not? So it's giant, 7,000 tons. And I still remember the superconducting super collider, which was cancelled in 1993 after $2 billion was spent to establish it in a site near Dallas, Texas. Those were, as we look at problems we see today, we have to remember, life was not always perfect for researchers. We had difficulties and had to express ourselves and explain why it was important. The field I was in, particle physics, was notorious for not doing such a great job explaining why it was important. Actually, it's sort of funny how Google Scholar tells you what you did, what's good. If I look at Google Scholar, I see this paper here, which in 2019, today, had 1607 citations. And when I happened to print this, Google Scholar had actually a better printout in 2013. Only 1143, so it's gone up. That's not because over 450 have cited it in the last few years. It's because Google has discovered more citations, or what it thinks is citations. And so this says that this particular paper, which is actually on data science for this field, to try to understand what the structure of the quarks were from the structure of the momentum vectors of the observed particles. I did with somebody who's far more important than me, Stephen Wolfram, who set up the Wolfram Company, the Mathematica software. Mathematica was actually funded by my personal research, my Department of Energy research group, and I worked with Stephen on that for a year or so. And we published many papers together. Whole set of them. You will find them mainly at this place here, stephenwolfram.com. Some of mine are available from ResearchGate and things like that. All right, so this is data science for such experiments from on a personal note. And here is another legacy from the past, which I enjoy. Work I did with Feynman and my postdoc, Rick Field, who just retired from Florida, Gainesville. And it is on the physics of such experiments which discover the Higgs boson. So as far as I know, the physics he did was correct. It was sort of irrelevant because when we were doing it in 1978, we were not, obviously LHC didn't exist. We were looking at much harder places to discover the Higgs. We were not actually looking for Higgs, we were looking for quarks and gluons and things like that. And this only had 300. This actually has a different citation spectrum. Most of the citations were nearest publication date, and it just has a few kind people who cited us in the future. Actually, 399 has gone up to about 465, and you can still see it gets cited most years. There's 2019 still an occasional citation. Notice that in 2013, Google Scholar gave you a picture with all the years. Now they give you a sliding window, which I can't make a screen dump of, and you only get here, whatever it is, 15 years or 12 years displayed. Anyway, it's always good to know that the work you did, and this was in the late 70s mainly, still has some relevance today, but also see how long it took to test it. 20, whatever it was, 5 years ago they discovered the Higgs. Well, that was a long time after we discussed it. Well, I didn't mainly work on the Higgs, I mainly worked on quarks, but they're all part of the same cosmic theory, all discussed in those mid-70s, early 80s timescale. All right, so that's it. My personal take on these things. We move on. This is why I gave up physics. This is just the A's and the B's of the Atlas collaboration. So you can see this particular paper is dominated by the list of collaborators. Amazing. So you can go on and see all the other collaborators. But it's an incredible feature of science is the enormously large teams. Sort of important but daunting fact. Thank you. So that's the end of this particular lesson. Thank you.